Newton's second law. Alright, so Newton's second law is functionally just a statement of mathematical fact, unlike the first law, which is sort of a more vague statement about what happens in general. Newton's second law says that the acceleration of an object is directly proportional to the force, the net force, the sum of all forces on the object, and inversely proportional to the mass of the object. For A is equal to sum of F divided by M. Or, the way we normally write it, the sum of forces is equal to M times the acceleration. Okay, we find that this is very familiar if we think back on the first law, because if there is no net force, then sum of forces equals 0, which means we would anticipate there would be no acceleration. No acceleration means no change in motion, means no speeding up or slowing down. So the first and the second law are a little bit talking over each other. They're kind of saying the same thing, though. Alright, this equation is properly a vector equation, which does have many consequences. It means that the forces don't need to be all in the same direction. They can be in different directions. They can be along completely different axes. It also means that we can split this equation up and think about the sum of forces in x is equal to m times the acceleration in x, and the sum of forces in y is equal to m times the acceleration in y. It's completely separable into two pieces, just as the motion in chapter 4, or the motion in our 2D kinematics chapter was. They're pretty much following the same pattern here. I mean, all vectors do. It's not really a surprise. All right. That vector idea is very important. If we have a single object and we have a force 1 acting in one direction, and a force 2 acting in a different direction, and a force 3 acting in a third direction, we can actually think about, I think I want to change color for this part, we can actually think about the angles that each of these forces would be at, and we can look at decomposition. So we can find the net force in x, which would look something like F1 cosine theta 1 plus F2 cosine theta 2, at least with the way theta is defined in this case. Similarly, with the y component of the force would just look something like F1 cosine theta 1 plus F2, oops, sorry, not cosine. Got to be careful with that. The sine would be along this side, the vertical side. So F1 sine theta 1 plus F2 sine theta 2 plus, or rather in this case minus, an F3 which points straight down. So again, we can just divide things up into components and figure out what is going on. Alright, thinking about this, there are a couple interesting ideas I want to hit quickly from the practice sheet. One of them has to do with this first thing here. One of these two pictures in the first one is talking about when an object or a car or a crash test dummy in a car is in a car that is undergoing a head-on collision, and when it's in a car that is undergoing a rear-end collision. And this one down on the bottom here, that one is actually the one for hitting head-on. So remember, the first law says an object in motion remains in motion unless acted upon by a force. So in this case, you're going forward, you're going forward, you're going forward, something stops the car, which stops the seat, which stops your body, which your head keeps going forward until your spine can bring it to rest. The other picture would be showing a rear-end collision, where you're sitting still, you're sitting still, you're sitting still, something hits the back of the car, starts the car moving forward, which starts the seat moving forward, which starts your body moving forward, and your head gets left behind until the spine can get a strong enough force on it to drag it along. Okay, the other one to look at here is the second question. A box is pushed to the left at a constant speed of 5 meters per second. So, constant, 5 meters per second, and it also states to the left. It further goes on to say, you exert a force on it, or the person exerts a force on it, of 100 newtons. Then we're asked the following questions. Any other forces? How can you tell? And finally, the other force, what is its size and direction? If there is one, which the question is clearly hinting there will be. Alright, but how can we use the second law to be absolutely sure? First, constant 5 meters per second to the left is telling us the acceleration is 0. Why? The speed and the direction, neither one are changing. No change in speed or direction, no acceleration. Alright, the rest of it. Sum of forces must therefore be equal to 0. But we know we have at least one force to the left. So we've got 100 newtons to left, blah blah blah, and equals 0. Well, there's clearly a problem there. We can't have 100 newtons to the left equals 0, so there must be some other force. That other force needs to be such that it cancels this out. So, yes, there's another force. How can we tell? Because there's no other way to get 0 for the acceleration. That other force must be 100 newtons to the right. Okay. So, very typical way of thinking about these things. Let's talk about a couple other examples. Forces are purely additive here. If we imagine one person can exert a 5 Newton force and another person can exert a 10 Newton force, then if they both act on the same object, we get a total force of 15 newtons. And let's say the object has some mass. I think I'm going to go with 5 kilograms here. So we could actually use this to find the acceleration, which would be the sum of forces over the mass, and in this case would be 3 meters per second squared. Using the idea that the sum of forces equals ma, Newton's second law. And we can think about a couple other examples. What would happen if they were trying to act in opposite directions? Or switch it around the other way. So here we'd take the difference, we'd have a net force 5 newtons to the left, and we'd find the acceleration is minus 1 meter per second squared. Going the other way, we'd find, of course, 5 newtons, and the acceleration would look something like 1 meter per second squared, towards the right in this case. And I forgot, my camera's reversed, so now I have to point to my left in order to you to see me pointing towards the right. I have kind of looked into if I can switch that with the tools that are built in, and I'm sure there's a way to do it, but I haven't figured it out just yet. It's probably staring me right in the face. Okay, again, it is a vector thing, so we could take and set the 5 Newton force and the 10 Newton force perpendicular to each other, in which case the magnitude of the acceleration would be 5 squared plus 10 squared newtons, and the direction of it we could just take inverse tangent of 5 newtons over 10 newtons. So all the same vector rules apply. Okay, I think this is just about everything I'd want to say about Newton's second law. For now, we'll have more to say about it once we do proper free body diagrams. And that's going to be it for this video. I'll see you in the next.